All right. At first glance, you may be looking at this lesson title and asking yourself, wait a minute, I feel like we've already talked about parabolas. I feel like we've talked about parabolas a lot in this course. And we have. We've done quite a bit in our study of polynomial functions like quadratic functions and such. But I want to just look at parabolas from another lens in this lesson because a parabola is another type of conic section. And right now we're exploring different conic sections. And if you recall, and if you watch my previous video, we said that a conic section not only is the intersection of a plane and a double napped cone, but it's the set of all points in a plane that satisfy a certain criteria. With a circle, for example, we said it was the set of all points that are equidistant to a fixed point, which we call the center. And every conic section that we're going to explore is going to have its own set of criteria for the set of all points. For a parabola, it's going to sound a little complicated at first, but just bear with me. Let me break down, using this image here, break down for you how we would define a parabola as a conic section. So we already know what a parabola looks like. So we've got this here. This is our parabola, right? We know it's the graph of a quadratic function. Now, instead of focusing on it being the graph of a quadratic function, I just want to highlight a couple of key parts of the parabola, some parts that actually existed that we haven't discussed too much so far. We already know about the vertex, and the vertex we said when it was a parabola that was opening up or down represented the lowest or the highest point of the parabola. So when our parabola was opening upwards here, we see that our vertex in this particular case represents our minimum or our lowest point. Now, inside every parabola, there's something called a focus. It's a point that exists inside the parabola, and it actually exists on our axis of symmetry here. So let me actually just go ahead and do this and just draw the following. So we've got an axis of symmetry, and let me actually make that a little bit larger so we can see that here. So let me make that a little bit larger. Okay, so inside every parabola, we have the axis of symmetry, which again works to separate the parabola into two symmetric parts. We know that the vertex lies on this axis of symmetry, but also on this axis of symmetry, there is something called the focus here. And a focus is a point that lies on the axis of symmetry. And the distance, and I'll go ahead and redo this, the distance from the focus to our vertex here, this distance here, we're going to call this distance, so we're often label it as our p-value, but we'll come back to that a little bit later. Perpendicular to our axis of symmetry, so perpendicular to our axis of symmetry, is a line that is called the directrix. The distance from our focus to our vertex is equal to the distance from our vertex to the directrix. So you can kind of imagine the vertex being the exact center in between the focus and the directrix. Okay? So the way we then define a parabola is the set of all the points in a plane that are equidistant from the fixed line, which is the directrix, to our focus, which is a fixed point that is inside our parabola. What does that mean? It means I can choose suppose I have this point right over here, and I would say, all right, what is the distance from that point to the directrix? What is the distance here? So we'll call this here in this case D3. I'm just going to label that distance here from D3. The distance from this point to the directrix is then congruent or equal to the distance from that point to the focus. Any point that satisfies this criteria, any point that is equidistant to the focus as it is to the directrix, is a point that is on our parabola. And that is how we define a conic section. It is a set of all points in a plane that are equidistant from the directrix and the focus. So we've got this labeled in a number of different places. So if I take this point, for example, if I find another point and I see that distance to the directrix is D1, and that distance is also the same as the distance to the focus, that is a point that exists on our parabola. So it's just another way of looking at a parabola. We already know it as the graph of a quadratic function, but now we see it satisfying a set of certain criteria, which makes it a conic section. If we move to this part of our notes here, I've just gone ahead and provided an image that talks a little bit about what the values, in this case of P and H, all that stuff tells us. The vertex of our parabola is again going to be the same variables that we use when we describe the center of a circle, so H and K. As I said, our P value is the distance from your vertex to your focus, and it's also the distance from your vertex to the directrix. When your p-value is positive, that means that the focus is inside your vertically opening parabola. When our p-value is positive, that means, in other words, our focus is on top of our vertex here. I'm focusing on this image here. See what I did there? I'm focusing on this image. I deeply apologize. So when our p-value is positive, our focus is on top of our vertex. That means our parabola is opening up. When our p-value is negative, that means our focus is underneath our vertex. And so now you have a parabola that opens downward. You might be somewhat familiar with these forms for a parabola. Here, when our x value is squared, when our x value is what's quadratic, that means this is y as a function of x, which would make this parabola vertical, meaning it opens up or it opens down. On this side here, you'll notice that when our y values are squared, when our y values are squared, that means now x is a function, we can write this, x is a function of y. X is a function of y, in which case that means our parabola is going to be opening to the right or to the left. And again, when our p-value is positive, our focus is inside our parabola. That means it's opening to the right. It is to the right of our vertex. When our p-value is negative, our focus then is to the left of our vertex. So you can pause the video or just consult the notes there and see what I have written down here. Just reviewing my conversation just now about what our H and P values tell us about our parabola, and also whether or not x is squared or y is squared, because then that determines whether or not our parabola opens vertically or horizontally, respectively. Everything that I've described here is summarized for you here. So again, if you don't have a copy of these notes, you can pause and write these down, or you can just check my classroom, and I will have all of these uploaded there. Now let's have a conversation talking about the new standard form versus the old standard form of a parabola. As I mentioned earlier, we've already worked with parabolas quite a bit. We've seen them. What was our old standard form? How did we write parabolas before? Well, we typically said the following. We said when it was a vertical parabola, we said y minus k is equal to a times x minus h squared. Or you might have seen this as y is equal to a times x minus h squared plus k. We're just moving that value of k over to the other side. We've seen it either one of those ways. When it was a horizontal parabola, we said x minus h is equal to a times y minus k squared. Now, these old standard forms were great for graphing because it told us our vertex pretty easily, and we could see whether or not our leading coefficient was positive or negative, which told us whether or not it opened up or down. In the context of conic sections, we then write it as the following. When it's vertical, we say x minus h squared is equal to 4 times, again, our p-value, which represents, again, our distance from our vertex to our focus, times y minus k. And when it's horizontal, we say y minus k squared is equal to 4p x minus h. We could also write versions of these forms when our center is at the origin. So when our center is at the origin, I'll just write that for our origin there. We would say x squared is equal to 4py. That means our h and our k values are 0. And y squared is equal to 4px. So comparing the two, what's the benefit of each? The old standard form was great for graphing because it told us things like our behavior of our function pretty easily. The new standard form tells us our focus and our directrix really easily. And pause the video and ask yourself real quick, what is the relationship between A, let me highlight these, between A and 4p? What would be the relationship there? Now, at first glance, you might think A is equal to 4p, isn't it? But not quite, because notice where the A and the 4p values are. The 4p is in front of the, well, I should maybe highlight the appropriate one so that we're not so confused. Notice where the A and the 4p values are. In the old standard form, the A is a coefficient of x minus h squared. In the new standard form, 4p is in front of the y minus k. So A is actually equal to 1 over 4p. Okay? So hopefully that kind of breaks down for you a little bit of the differences between the two forms that we're accustomed to seeing. Now let's jump into working with equations and writing the standard forms of them. So let's practice going from regular form to standard form. So let's take a look at this first equation here and ask yourself, what form are we currently in? We say y is equal to ax squared. Well, that looks like our old standard form, right? Y is equal to ax squared. And again, one thing that's nice about this is right away we see that in this particular case, our a value, which I'll highlight here, a is equal to -1/4. And so therefore we know that this is going to open downwards. Right? This is going to be a parabola that opens downward. Also because our degree is, our x value is what is squared. So if our x variable is squared, that means y is a function of x. So it's going to be vertically opening downward in this case. Okay, but that's just stuff that we can kind of tell by looking at this equation. Let's go back into start thinking about, all right, how would we write this in our new standard form? Well, we want this to look like what we have up here. And we know, again, that this is vertical in this particular case. So we want to have our x value squared by itself, isolated. So here we're going to multiply both sides by -4. So we say -4y is equal to x squared. So if I just want to be cleanly aligned with what I have written up there, we'd say x squared is equal to -4y. And that's it. This is a pretty simple problem, actually. Well, from this, what can we tell? What can we determine? We're asked to do quite a bit here. We already figured out the standard form, but let's also figure out our vertex, axis, focus, and the directrix. Okay, let's start with our vertex since we already have the standard form. So for our vertex here, what do we know? Well, we know that our vertex, our h value appears to be 0, and our y appears to be 0 because we're not subtracting any number other than 0 from x or from y. So our vertex is just at 0, 0. Next up, what about our axis of symmetry? What do we know about our axis? Well, our axis is just the line that goes through our vertex. Since this is a vertically opening parabola, we know that it's going to be x is equal to 0. And as I go along, I might as well actually graph this so I can keep this up. So we know the vertex of our parabola is at 0, and we know that our axis of symmetry, let me make this a little bit larger, is going to go x is equal to 0. So I can draw that there. Okay? All right. What do we have next? Let's move on to the next part. What about the focus? What do we know about the focus? Well, to know where the focus is, we need to know what our p-value is. And what do we see? We can see there, let me just go ahead and switch this back. We can see here that -4 is going to represent our 4p. So -4 is equal to 4p. That means p is equal to -1. Since our p-value is less than 0, therefore we know, again, it is opening downwards. It's opening downwards. Our p-value is, our focus is going to be inside our parabola or below our vertex. So we can say that our focus is going to be 0, -1. So 0, -1 down here. All right. Since now we know our focus, we can do our directrix pretty easily now. The directrix is going to be on the opposite side, or here. And let me go ahead and adjust this. We can see that our directrix has got to then be on the opposite side of the vertex. Let's switch this back. So our vertex is going to be the line It is a line, not a coordinate, so y is equal to 1. So there's our directrix. So we've got mostly everything here. Right? Now let's just finish this off by graphing. Well, we already know our focus, we know our vertex, so all we really need to do is plug in a couple of points on either side of the parabola and just go ahead and reflect them. For the sake of time, I'm going to trust that you know how to plug in points here. For example, if you plug in the x value of 2 into your equation here, we would be able to find different y values that we can kind of plug in. So I'm going to do something like this here. When x is equal to 2, for example, I'm going to get y is equal to -1. You can use either form. This is why the old standard form is good for graphing. Again, when x is equal to 2, -1/4 times 4 is equal to -1. And I can do other points like when x is equal to 4, I know that y is equal to -4. And really just about 2 points on each side other than the vertex are pretty good. You can do more if you want to be more precise. But from here, I should be able to graph something that looks like this. And that means I can just reflect those points and write these down here. And that's good enough for a rough sketch of our parabola here. Okay? All right, let me do one more with you here. Let's go ahead and take this equation and let's write it in standard form. Notice right off the bat that our y is what is squared. Notice our y is what is squared. So that tells me right away that this is going to be a horizontal parabola. It's going to be opening either to the left or to the right. So if I want this to look like y minus k squared is equal to 4p x minus h. So I want this equation to look like it's in this form. So again, we're going to need to complete the square. So let's write y squared minus 2y plus some value. And let's go ahead and move our x and constants over to the other side. So we've got 2x plus 3 and plus whatever we add there in order to complete the square. Well, what do I need to complete the square? Half of -2 is -1. -1 squared is +1. So we're also going to add that over to the other side. And so this gives me y minus 1 squared. We can simplify this as 2x plus 4. But to fully write it in standard form, we're going to need to factor out that 2 there. So we're going to write y minus 1 squared is equal to 2 times x plus 2. And here's our standard form. And again, what's nice about this standard form is that it gives us key information like our vertex, focus, axis of symmetry, all that stuff, pretty easily. Again, keep in mind that this here is our 4p, so 4p is equal to 2. That means p is equal to 1/2. Since this is a horizontal parabola, that means our parabola is going to be opening to the right. Our focus is going to be to the right of our vertex. So let's go through and let's see what information we can glean from our standard form. Pause the video right now and see if you can list out things like the vertex, the axis, the focus, and the directrix. Well, our vertex is going to be -2, +1. Our axis of symmetry is going to be y is equal to 1. It's the line that runs through vertical part of our vertex. Our focus, well, and perhaps I should graph this as I go along so we can see this. If our vertex was at -2, +1, and I know that my axis of symmetry is here, y is equal to 1, and I know my parabola opens to the right, that means my focus then is going to be to the right of my vertex, which means I have to add +1/2 to my horizontal component, my x coordinate. So -2 plus 1/2 is going to be -3/2. And my y coordinate stays the same. So this might be a little bit tricky to see, so I'm going to just underline my focus. It would be right there, half a unit to the right of my vertex. My directrix would then be x is equal to -5/2. So I'm going to draw a vertical line that goes like this. Again, draw these dotted because these are guiding lines. These aren't values of the function. And just like we did before, now all we need to do is plug in values into our function and reflect them over. So for example, when x is equal to 0, y would be equal to 3, for example, and I can reflect that over here. And if I plug in another point, let's see, something like this and this here, there should be another point. If I reflect that over, I should get this point right over here. And this should be good enough to create my parabola, or at least a rough sketch of it. Okay?